Let's do our second lesson on vectors, where we learn how to add and subtract vectors. In the first lesson, you should have learned what a vector is. So a vector is something that has both a magnitude and a direction, and it can be represented geometrically with a directed line segment. Typically, we label the tail of that directed line segment with a letter, so I'll call it A for this vector I made here, and we label the tip of the directed line segment with a different letter. I'll call it B. So this vector AB has a very specific magnitude represented by the length of that line segment, and a very specific direction represented with the arrowhead at the tip B. And the notation for representing this vector would be this: AB with a vector symbol above it. That means we have vector AB, a vector that starts at A and finishes at B. Now what we're going to do is look at, okay, what if we have multiple vectors and we want to add or subtract them together? We'll start with adding. When you add two or more vectors together, we find a single vector, and we call that single vector the resultant vector. And that resultant vector has the same effect as the original vectors applied one after the other. Now there are two methods for adding vectors. Really, they're the same thing, just kind of different ways of thinking about it. I'm always going to talk about the tip to tail method, so that's what I'll review with you right now. But if you want to learn the parallelogram method, feel free to pause the video and look over that right now. All right, let me teach you the tip to tail method. So if we want to add vector A and B together, so notice in the diagram below, I have it showing you vector A, vector B, and the resultant vector, vector A plus vector B. Let's read this section, which tells us how we can set up that diagram. The sum of vectors A and vector B can also be found by translating the tail of vector B to the head of vector A. The resultant is the vector from the tail of A to the head of B. So let me show you the process you would go through to create this diagram. So I've redrawn vector A and B below. Notice vector A, same magnitude and direction, I've just translated it down here. And vector B, same magnitude and direction as vector B, I've just translated it down here. You're allowed to move vectors wherever you want as long as you keep their magnitude and direction the same. All right, now if we want to figure out vector A plus vector B, what we have to do is translate vector B without changing its size or magnitude so that its tail is at the tip of vector A. Notice how I've moved it, but its direction and magnitude have not changed. These vectors are now tip to tail. This is why this is called the tip to tail method. It's useful to put them in this position because once they're in this position, the resultant vector, vector A plus vector B, is the vector that goes from the tail of the first vector, vector A, to the tip of the second vector, vector B. So vector A plus vector B would look like this, from the tail of A to the tip of B. That would be our resultant vector, vector A plus vector B. And notice that resultant I got is the exact magnitude and direction of the resultant it shows us in that diagram. I just added this slide in here to get you to think about what would happen if we added opposite vectors. Now, what are opposite vectors, first of all? Opposite vectors are vectors that have the exact same magnitude, but are going in the exact opposite direction. So when two opposite vectors are added, the resultant is what we call the zero vector. And below you can see I've drawn two opposite vectors. I've drawn vector AB, which starts at A and finishes at B, and vector BA, which starts at B and finishes at A. Notice those two vectors have the exact same length. They're the exact same magnitude, but they're going in the exact opposite directions. One's going from A to B, the other's going from B to A. So we call those opposite vectors. Now what would happen if I added those vectors together? What if I did vector AB plus vector BA? If I did the tip to tail method, I would have to take vector BA and place it so its tail is at the tip of vector AB. So it would look like this. Now I'm going to separate them a bit just so you can see what I'm about to talk about next. If I were to try and draw the resultant vector, it would be the vector that goes from the tail of AB to the tip of BA. Well, those two things are in the exact same spot, so I wouldn't be able to draw a vector, so I'd say the resultant is the zero vector. How I could prove to you algebraically the result is the zero vector? Well, what I could do is rewrite this equation as vector AB plus, I'm going to change vector BA to negative vector AB. And I know that would equal the zero vector. Why am I allowed to change vector BA to negative vector AB? Well, to explain that, you need to understand what the effect of multiplying a vector by -1 would do. It wouldn't change its magnitude. It would keep its magnitude exactly the same, but it would reverse its direction. So negative vector AB means a vector that has the same magnitude as AB, but is going in the opposite direction of AB. What vector would that be? That would be vector BA. That's why I was able to rewrite vector BA as negative vector AB. And now you can see, if I were to simplify adding a negative, well, that's just minus, so I have vector AB minus vector AB. Of course, that resultant is going to be 0. And when dealing with vectors, we say 0 vector. Part 2, difference of two vectors. So now that you know how to add vectors and you know what opposite vectors are, we should be able to figure out two different ways to subtract vectors. I'll show you both. The first one is called adding the opposite. And now that we know what opposite vectors are, you should be able to do this one. So if my goal is to figure out vector A minus vector B, and over here I see vector A and vector B, let me just redraw them below so that I can translate them. Okay, here we go. I've redrawn vector A and vector B, and keep in mind my goal is to figure out what is vector A minus vector B. And there's two ways to do this. Let me explain to you the adding the opposite way first. So I'll demonstrate it, and then I'll go back up and read the definition to you. So if we want to do vector A minus B, well, we know how to add vectors, so I could change this to an addition question. I could change this to an equivalent expression using addition. So this would be equal to vector A plus the negative of vector B. Right, adding a negative is the same as subtracting. So hopefully you can see why that line is equivalent to the one above. And now I can use my tip-to-tail method of adding vectors. So I need to do vector A plus the negative of vector B. Well, what is the negative of vector B? The negative of vector B would be a vector that has the exact same magnitude as B, but goes in the opposite direction. So there we go, that's negative vector B. It's the exact same magnitude as B, but is now going in the opposite direction. And now I just have to add these two vectors. If I want to do vector A plus negative of vector B, the tip-to-tail method tells me that what I do is I take the tail of negative B and put it at the tip of A to look like this. And then the resultant vector would go from the tail of my first vector, so from the tail of A, to the tip of my second vector, so to the tip of negative B. So the resultant would look like this. That would be vector A minus vector B. And notice if I bring this up to this diagram, notice that it's the exact same magnitude and direction. So what did I just do to find vector A minus vector B? I did what's called adding the opposite. The difference between A and B is found by adding the opposite of vector B to A, using the triangle law of addition, which is sometimes called the tip-to-tail method. And notice when it's set up as A plus the opposite of B, so A plus negative B, what we get is A minus B. And what I got is the same magnitude and direction of what's in the diagram there. Okay, let me redo this question a different way. So I've reset the two vectors. So I'm back with just regular vector A and vector B. And I'm going to show you the other way that we can find vector A minus B. So instead of adding the opposite, what I could do is take vector A and B the way they are and translate them so they are tail to tail. If vectors are placed tail to tail, the difference between the two vectors can be found by drawing a vector that goes between the tips of those vectors. And the direction is very, very important. If we're doing A minus B, the tail of vector A minus B has to be at the tip of the vector that's being subtracted. So it has to be at the tip of B. And the tip of A minus B has to be at the tip of the first vector. So in this case, vector A. So that would be vector A minus B. So in this method for subtracting vectors, you position the vectors that are being subtracted tail to tail and draw the difference of those vectors with a vector that goes between the tips of them. The direction of that vector is important though. If you're doing A minus B, notice vector A minus B has its tip at the tip of vector A. If we were doing, let's say, B minus A would have the exact same magnitude of this but be in the opposite direction. B minus A would have its tip at the tip of B. And notice the result I got with this method is the same as we got the other way. Doesn't matter, those two vectors are the exact same magnitude and direction. So there are two methods that get you the same result. So either add the opposite or do the subtraction method where you place the vectors tail to tail. Now that you know the rules for adding and subtracting vectors, we can do some examples. Example 1, suppose we're given these three vectors, vectors a, b, and c that you see down below. Using these three vectors, let's sketch the graph of the vector that is vector a minus vector b plus vector c. When doing these types of questions, I find it most helpful if we change this to purely an addition question, because adding vectors is quite easy. So I'm going to rewrite this in an equivalent form. Instead of doing vector a minus vector b, I'm going to do vector a plus negative vector b. Right, that's the same. One method for subtracting vectors is to add the opposite. And now that I rewrote the question in an equivalent way where it's purely the addition of three vectors, I can just translate these three vectors on the screen so that they're tip to tail with each other and then get the resultant by going from the tail of the first vector, so the tail of vector A, to the tip of the last vector, vector C. So let me show you how that works. Now, I'm going to be able to move these vectors around on my screen. And when I do that, I'm keeping their direction and magnitude the same. But you obviously can't do that on your paper, so you'll have to do your best to redraw these vectors in a way such that its direction and magnitude does not change. Okay, so if I want to do the sum of these three vectors, well, first of all, I'm going to have to get negative vector b. So what I'm going to do, I'm going to copy and paste vector b. And down here, I'm going to change this bottom one to negative vector b. And how do I do that? I keep its magnitude the same, but make it go in the opposite direction. There we go. Down below, I now have negative of vector b. Same magnitude as vector b, but it's going in the opposite direction. Okay, so now I can reposition these vectors so that I have vector a plus negative vector b plus vector c. So to do that, I would take negative vector b and place the tail of it at the tip of vector a. And now I need to add vector c to those two. So I'll place the tail of vector c at the tip of negative vector b. Okay, so when adding vectors, we place them all tip to tail. And now the resultant vector goes from the tail of the first vector to the tip of the last vector. So it's going to go from the tail of vector a to the tip of vector c. So my resultant vector would look like this. That would be vector a minus vector b plus vector c. Okay, let me show you quickly another way we could have gotten vector a minus vector b plus vector c without doing the add the opposite method. I could have subtracted vector a minus vector b by placing them tail to tail and drawing a vector between the tips of the two. So vector a minus vector b would go from the tip of b to the tip of a. So it would look like this. That would be vector a minus b. And then to vector a minus b, the question says we then need to add vector c. So I need to add vector c to this red vector here. And when adding vectors, you place them tip to tail. And the resultant goes from the tail of the first vector to the tip of the second vector. So it would go from the tail of a minus b to the tip of c. And that red vector would be equal to a minus b plus c. And what I want you to notice is that it got us the same result. I mean, there's a little bit of variability due to, human error, but it gets us the vector going in the exact same direction with the exact same magnitude. So both methods get you the same result. Wouldn't matter which of those two methods you used. Example 2, in the rectangular box shown, vector OA I've called vector A, vector OC I've called vector B, and vector OD I've called vector C. I want you to express each of these following 6 vectors in terms of vector A, vector B, and vector C. So we'll write it as, the sums and differences of those 3 vectors. Let's start off with vector BC. So let's look at vector BC. So there's vector BC, what I've drawn there. Notice that vector is the exact same magnitude as vector A. It's just pointing in the opposite direction. So I could say that vector BC is equal to negative vector A, right? Because it's the same magnitude, just opposite direction. So BC equals negative vector A. How about part B, vector GF? GF is this vector up here. Well, actually notice that vector is exactly equal to vector A. It's the same magnitude and direction. So vector GF is just equal to vector A. How about vector OB? So the vector that goes from O to B. This vector, okay, well this one doesn't look like it's equivalent or opposite to either A, B, or C. But maybe I could express this as the resultant of the sum or difference of vectors A, B, and C. So what I mean by that is, I need to figure out, are there a combination of vectors that I could place together so that it would equal vector OB? Now, I could express it as a sum of vectors if I can place some vectors tip to tail so that the tail of the first vector is at O and the tip of the last vector is at B. And there's a couple ways we could do that. I could start at O and go over here to A, and then once I'm there, go from A to B. Notice the resultant of those two motions, going from O to A and then A to B, has taken me from O to B. Therefore, the sum of those two blue vectors is equal to vector OB. So what are those two blue vectors? Well, the first one I drew is equal to vector A, and the second one appears to be equal to vector B. Let me compare. Yes, it is the same as vector B, same direction and magnitude. So this I could call vector B. And notice that vector A and vector B are placed tip to tail, so the resultant would go from the tail of the first vector to the tip of the second vector, and that resultant is vector OB. So I could say vector OB equals vector A plus vector B. Part D, we want to come up with an expression for vector AC in terms of vector A, B, and C. So AC, that would look like this vector right here. So I need to figure out, how can I get from point A to point C using vectors A, B, and C? Well, if I were traveling from point A to point C, one way I could do it would be to go from A to B and then from B to C. That would work. The sum of those two blue vectors equals the red vector, right? The blue vectors are placed tip to tail, so the resultant will go from the tail of the first vector to the tip of the second vector. So those two blue vectors added together equal vector AC. Now I need to figure out, well, can I write those two blue vectors in terms of vector A, vector B, and vector C? And in fact, I can. Vector AB appears to be equal in magnitude and direction to vector B. So I could call this vector B. And vector BC appears to be equal in magnitude to vector A, but in the opposite direction. So I could say vector BC equals negative vector A. So I could say vector AC equals vector B plus negative vector A, which of course we could simplify that to just vector B minus vector A. And if you're really good at subtracting vectors, you may have seen that right off the bat. Notice this vector AC could be represented as vector B minus A, because if we placed vector B and A tail to tail, vector AC has its tail at the tip of A and its tip at the tip of B. So we could express that as vector B minus vector A, which is what we got as our answer, vector B minus vector A. There's lots of ways to think about these problems. Let's move on to part E, which asks us to do vector BG. Means tail at B, tip at G, so it would look like this. I could express that as a sum or difference of a bunch of vectors. Let's just pick one way to do this. To get from B to G, I could first go from B to F, and then from F to G. That's one way to do it. Notice vector BF and FG are placed tip to tail, so the sum of those two vectors would equal the resultant vector, vector BG. So now let me see if I can rewrite vector BF and FG in terms of vectors A, B, and C. Well, vector BF, notice that is the exact same magnitude and direction as vector C, and vector FG is the same magnitude as vector A, but the opposite direction, so FG I could say is equal to negative vector A. So vector BG equals vector C plus negative vector A, which once again we could simplify to vector C minus vector A. And lastly, vector OF, tail at O, tip at F. Let's see how I could express this as a sum of vectors. I would need to start at O, and then I could first, well, there's lots of first moves I can make, but how about I go from O to A first, and then from A to B, and then from B to F. That's probably the easiest way to do this. Notice that the sum of those three blue vectors I drew, since they're all placed tip to tail, is equal to the resultant vector OF. So now let me just express all those blue vectors in terms of vectors A, B, and C. Well, vector OA is vector A. Vector AB is the same magnitude and direction as vector B, so I could relabel this vector B. And vector BF is the same magnitude and direction as vector C, so I could label this vector C. So vector OF is equal to the sum of vector A plus vector B plus vector C. Let me go over some properties of vector addition with you. The first property, the commutative property, states that vector U plus vector V equals vector V plus vector W. When you think commutative property, think about moving. In an expression where vectors are being added, you can move around the order of the vectors and it still equals the same thing. The next property, the associative property. When you think of associative property, think of grouping of vectors. We can group them in different orders and we would still get the same answer. So you can see that demonstrated to the right here. Vector U plus vector V, if we group those together and find the resultant and then add vector W, we would get the same answer as if we first grouped vector V and vector W together and then added vector U. And then our last property, the identity property, tells us that if we add the zero vector to a vector, we're left with just the original vector. So vector V plus the zero vector is just equal to vector V. And also because of the commutative property, we know that that would also be equal to the zero vector plus vector V. So with these properties, we should be able to simplify the following expressions. Vector U plus vector V minus vector U. Well, if I use the commutative and associative property here, I'm going to rearrange the order of these and regroup them. So I'll rearrange the order of U and V. That would be V plus U. That's the commutative property. Now I'll do the associative property and regroup these. So I can do vector V plus vector U minus vector U. And vector U minus vector U, that is the zero vector. And vector V plus the zero vector is just vector V. All right, let's do the same thing with part B. I'm going to use the commutative property and rearrange the order of vector P plus vector Q to give me vector Q plus vector P. And now I'm going to use the associative property and regroup the vectors in the square brackets. I'm going to group the vector P's together, so I'll have plus vector P minus vector P. And vector P minus vector P, well, that's the zero vector. So I've got vector Q plus the zero vector minus vector Q. And vector Q plus the zero vector, well, that's just vector Q. So I have vector Q minus vector Q. And a vector minus itself, that would be the zero vector. Now we're going to move on and do 3 application questions. Example 4, example 5, and example 6. Before we can do those application questions, I need to remind you about a few things. First of all, I need you to look at these 2 scenarios I have outlined here. If we have 2 vectors acting in the same direction, the overall magnitude is equal to the sum of the 2 individual magnitudes. So if we have 2 vectors working in the same direction, finding the magnitude of their resultant vector is easy. You just add the magnitudes of the 2 original vectors. If we have 2 vectors acting in opposite directions, the magnitude of the resultant would just be equal to the difference of the 2 individual magnitudes. Not all forces act in the same or opposite direction, however. So if we're trying to find magnitudes of resultant forces, we're going to have to remember some trigonometry rules. If we have a right angle triangle, rules that might be useful are the Pythagorean theorem, which tells us the sum of the squares of the shorter 2 sides equals the square of the longer side. For right triangles, SOHCAHTOA is also useful. It's useful if we know 2 sides of a right triangle and 1 angle, or if we know 1 side and 1 angle in the right triangle and want one of the other sides. If we have an oblique triangle, so a triangle that's not a right triangle, you'll have to remember sine law and cosine law. There are 2 scenarios for each of them. Sine law is useful if we have an oblique triangle and we know 2 sides and 1 angle opposite those 2 sides, or if we have 1 side and all of the angles. Cosine law is useful if we know 2 sides and the contained angle in an oblique triangle, or if we know all 3 sides of the oblique triangle. Now, typically we use sine law and cosine law when we have non-right angle triangles called oblique triangles, but those rules do also work for right angle triangles. However, Pythagorean theorem and SOHCAHTOA only work for right angle triangles. If you have an oblique triangle, you can't use Pythagorean theorem or SOHCAHTOA. Okay, let's do our application question. Example 4. Given vectors A and B such that the angle between the 2 vectors is 60 degrees, the magnitude of vector A is 3 and the magnitude of vector B is 2. Determine the magnitude of vector A plus vector B. So a few things here. First thing, when it says the angle between 2 vectors, that means if the vectors are placed tail to tail. So the way I would read this, it says the angle between vector A and B is 60 degrees. That means I know that if vector A and vector B replace tail to tail, the angle between them would be 60 degrees. Hence the way the diagram is set up to start off with. The next thing I see, it says the magnitude of A is 3. Remember, the absolute value symbols around a vector mean the magnitude of the vector, which means just its length. So I know the length of vector A is 3 and the length of vector B is 2. And we're interested in the length, the magnitude, of vector A plus vector B. So I'm going to have to construct vector A plus vector B and then find its magnitude using some trigonometry. To construct vector A plus vector B, well, to add vectors, they have to be placed tip to tail. So I'm going to translate vector B so that its tail is at the tip of vector A. So I'm going to move vector B, and now that they're translated so that they're tip to tail, I could draw the resultant vector, vector A plus vector B, by going from the tail of my first vector, so from the tail of vector A, to the tip of the second vector, so the tip of vector B. So this is vector A plus vector B. And I'm interested in the magnitude of that side. So to find the length of this side, I'm going to have to use some trigonometry rules. First thing, let me make sure I have labeled everything we know. I know the magnitude of A is 3, and the magnitude of B is 2. So I know in this oblique triangle, this one right here, this triangle here, I know two sides, but I don't know any of the angles yet. But if you remember your parallel line theorems, notice this C pattern. If you notice a C pattern, then there's a rule for the co-interior angles. This 60-degree angle and this angle here, I'll call it theta for now, they would have to add up to 180 degrees. So based on that property, I know theta would have to be 120 degrees. So I'm going to label this angle right here 120 degrees. And that co-interior angle rule only works if these two vectors are parallel. And it's the same vector, so of course they're parallel. Okay, so now look at what we have. Of this oblique triangle that I'm highlighting here, I now know two sides and the angle contained by those two sides. When that's the information that we have, we could use the cosine law to find the length of the side opposite from the angle that we know. And that's exactly what we want in this question. We want the length of vector A plus vector B. So if I use the cosine law tells me that the magnitude of vector A plus vector B squared would equal the magnitude of A squared, so 3 squared, plus the magnitude of B squared, so 2 squared, minus 2 magnitude of A times magnitude of B, so 3 times 2, cosine of the angle contained by the two sides, 120 degrees. So that's cosine law, and now we just evaluate this. So on the left, I'll leave the magnitude of A plus B squared. On the right, I have 9 plus 4 minus 12 times cosine of 120. Oh, and cosine 120, I could get an exact value for that. Remember your special triangles and your cast rule. If we were to rotate 120 degrees, that would land you right here with the reference angle of 60. And if the reference angle is 60, I know that's a special triangle where the side lengths are 2, 1, root 3. And based on cast rule, I know that the cosine ratio in this quadrant is going to be negative. So I could replace cosine 120 with negative cos 60, and cos 60 is a half, so I can replace it with negative a half. So the magnitude of vector A plus vector B squared equals 13, and then negative 12 times negative a half is positive 6. And now I'll square root both sides, and I don't have to worry about plus or minus square root because we can't have a negative length. So the magnitude of vector A plus vector B is just equal to the positive square root of 19, and then whatever units we're in. Example 5. An airplane heads due south at a speed of 300 kilometers an hour and meets a wind from the west at 100 kilometers an hour. What is the resultant velocity of the airplane relative to the ground? So the airplane's trying to fly due south at a speed of 300 kilometers an hour, but the wind is blowing from the west at 100 kilometers an hour. So what is going to be the resultant velocity of the airplane? Remember, velocity has a magnitude and a direction. So we're going to need to know the magnitude of the resultant and the direction of the resultant. So let's draw what the question gives us. It says the airplane is heading due south at a speed of 300 kilometers an hour. So the direction of the airplane is straight down, that's due south. And the magnitude of that vector would be 300 kilometers an hour. I'm going to call this vector vector v for the plane's velocity. The question also says that there's a wind coming from the west. If it says coming from the west, that means it's blowing east. So the direction would be straight to the east, and the magnitude of that vector would be 100 kilometers an hour. So since this is the wind, I'll call this vector w. The sum of the plane's velocity in the air and the wind's velocity is going to give me a resultant velocity of the airplane relative to the ground. So I need to add these two vectors together to figure out the resultant velocity of the airplane. So to add these two vectors, I have to place them tip to tail. So I'll translate the wind velocity vector so that its tail is at the tip of the plane's air velocity vector, and the resultant is going to give me what we call the ground velocity of the airplane. And the resultant would go from the tail of the first vector to the tip of the second vector. So from the tail of vector v to the tip of vector w. And for this question, I'll call this vector r to stand for the resultant velocity. I need to know both the direction of vector r and its magnitude, right? Because velocity has a direction and a magnitude. So let's start by finding its magnitude. Notice what we have here is a right angle triangle. We know two sides of the right angle triangle, so to find the third side, we could just use Pythagorean theorem. The magnitude of vector v squared plus the magnitude of vector w squared would equal the magnitude of vector r squared. So we'll do 300 squared plus 100 squared, and that will give us the magnitude of vector r squared. So it's about 316.2 kilometers an hour. So the wind is actually making the plane go slightly faster, but it's also changing its direction. What's its direction? Let's call this angle theta, and if I knew that angle theta, then I could describe this plane's new resultant velocity as a quadrant bearing. I could say south, theta towards east. So how do we solve for theta? Well, there's lots of ways. We have lots of excess information for this triangle since we now know all three sides. But if I use the two sides that I know exact values for, vector v and vector w, I could use SOHCAHTOA, since we have a right triangle, to find the angle. If we let theta be our reference angle, vector w is opposite and vector v is adjacent to it. So we would use tan. So we could say tan of the angle would equal the magnitude of the opposite side, so 100, divided by the magnitude of the adjacent side, 300. And if we want an angle and we know the ratio, to find the angle, we do inverse tan of the ratio, which is a third. So we'll do inverse tan of a third, and we're working in degrees for this question, so let's make sure my calculator is in degrees. I get about 18.4 degrees. So our final answer, we could say the resultant ground velocity of the plane is 316.2 kilometers an hour at a quadrant bearing of south 18.4 degrees east. Here's our last example, example 6. In an orienteering race, you walk 100 meters due east and then walk north 70 degrees east for 60 meters. How far are you from your starting position and at what bearing? So let's draw what the question gives us. It says I walk due east for 100 meters. So I need a vector going straight to the east where its magnitude is 100 meters. Let's say that's 100 meters. And then it says I walk north 70 degrees east. To draw that accurately, let me just draw in an invisible north line. To walk north 70 degrees east, that means from north, my vector is 70 degrees towards east. So it would look like this, and it needs to be shorter than my first vector because its magnitude is only 60 meters. So let's say that's about 6/10 of the other one. And I could fill in some information that I know. I know this is 60 meters. I know that's 90, and I know this is 70. The question says, how far are you from your starting position and at what bearing? So I need to know the magnitude and direction of the resultant vector. And the resultant vector would go from where we started to where we finished. I'll call that vector r because it's our resultant vector. If I want the magnitude of that vector, well, I'm working with an oblique triangle. You can see I have it highlighted here. There's our oblique triangle. In that oblique triangle, I know two sides and the angle contained between the two sides. So I could use, once again, cosine law to find the magnitude of the side across from the angle I know. So let me set up cosine law. It tells me that the magnitude of vector r squared would equal 100 squared plus 60 squared minus 2 times 100 times 60 times cosine of the angle that contains those two sides. 90 plus 70, that's 160, so cos of 160. And now I'll evaluate all of this and then square root it so that I can isolate the magnitude of r. Now, 160, I'm not going to be able to get an exact value for cos of 160, so I'll use my calculator to get me an approximate value. I get about 157.7 meters. So that's its magnitude, but what's its direction? I think I'll describe the direction of vector r using a true bearing. So true bearing is the angle between north clockwise to the vector. So I've drawn in another north line, and I'm going to describe the true bearing of vector r by figuring out this angle right here, theta. To figure out that angle, well, there's a few ways we could do it, but if you notice, I'll call this angle beta. Notice beta plus theta form a 90-degree angle. So if I can figure out beta, do 90 minus that, and I'll get theta. So let's start by figuring out angle beta. There's actually two ways I could solve for angle beta here. I could use sine law, do 60 over sine beta equals the magnitude of r, right, 157.7, divided by sine of 160. The only problem with doing that is when using sine to solve for an angle, you have to consider ambiguous case of sine. But to avoid having to worry about ambiguous case of sine, it's often better to use cosine law if it's possible to do it based on the information you have. And since I know the length of all three sides of the oblique triangle, I can use cosine law to find any of the angles I want. So based on cosine law, I could say cosine of beta equals, now we start with the side opposite from the angle we want, so 60 squared, minus the squares of the other two sides, so minus 100 squared minus 157.7 squared, all over negative 2 of the adjacent two sides, so of 100 and 157.7. Evaluate that ratio, do inverse cos of it, and we'll get beta. I get about 7.5 degrees. And remember, theta, if we look, theta would equal 90 minus beta, because the two of those angles are complementary. They form 90 degrees. So theta equals 90 minus 7.5, so we have 82.5 degrees. Theta, 82.5 degrees. So our final answer, we could say you have gone 157.7 meters at a true bearing of 82.5 degrees. All right, that's it for this lesson. Make sure you try the practice questions to get good at vector addition.